Introduction to Earth Science video. My name is Jeremy Patrich. I'm a professor of geology and geography, and I'm here to introduce this course to you. So, really, what is Earth science? Well, I think it's really exciting because, especially at a lot of the institutions that I work with, it's a required course for K through 12 educators as they're working towards their credential program. And I think a lot of individuals get nervous or scared about it because they don't want to take chemistry, they don't want to take geology, they don't want to take oceanography, they don't want to take meteorology or climate sciences, they don't want to take astronomy, so they think, oh, earth science, this will be an easy one to jump into. Well, surprise, surprise, earth science is all of those things lumped in together. We learn about the geology or study of the earth, we learn about oceanography and the study of our oceans, meteorology, understanding our atmosphere and weather. And we also learn about the study of our universe and our place within the universe. So Earth science covers a lot of different pieces. Each one of these is a normal 16-week course at most institutions. So we have to somehow merge all four of these topics into a palatable system. So it's going to be exciting, to know that we get to talk about so many different things. We're going to be able to talk about everything from climate to clouds to volcanoes, earthquakes, plate tectonics, solar nebula. I mean, pretty much everything you can think of is probably going to be brought up into this course. So it will be exciting and does cover a lot of content. But we'll make it palatable. We'll make it easier to understand, trust me. So let's look at each one of these a little closer. So the first one is geology, the study of Earth. So we break that usually into two pieces. We have historical geology and physical geology. So historical geology is really how do we understand Earth history. So as an example, you'll see there's a photo down here. This is me and some colleagues. We're actually excavating a left leg of a woolly mammoth that dated about 10,000 years ago in the eastern Sierra. So we started looking at some of the underlying geology, the sedimentology, understanding the environment in which he would have died in, because he actually died on a beach ridge made of fine-grained sands. So we start learning about the past. Again, you got to do your cliche, Instagram photo of the museum in natural history. But we get to understand the history and the fossil record, geologic time. Well, why is that important? Well, because once we understand that system, that evolution, we then bring into physical geology. How do we understand the processes above and below the surface and into the future? So we get to then look at this landscape in the middle. This is a photo I took of Ubehebe Crater in Death Valley National Park. It was a volcanic area. They're craters themselves, looking at steam vents. But looking at its past allows us to understand geothermal activity in other locations to learn about its future. The next one we'll look at is oceanography. This always excites me. I have a lot of friends who get to teach this course, and the first thing they say is students become often discouraged when they enroll in this course because they think it's about marine life. Well, that's marine biology. This is still an exciting course because it teaches you the coastal process, composition of the ocean. We learn about oceanic movement and seafloor topography. We learn about steam, the vents, volcanic vents. We learn about volcanic ranges and arcs, and so there's a lot more in the study of oceanography than just whales and dolphins. So we get to learn about the environment that they live in. We get to learn about how that environment interacts with our planet, and well, how do the oceans interact with our greater source? Perhaps even looking at astronomy in that sense. Well, when learning about what oceans are able to absorb, looking at greenhouse gases and things along that. It's really an exciting portion of this course. Moving into meteorology, really it's atmospheric sciences. How do we look at our planet's atmosphere? We acknowledge that we have four dominant layers that we deal with. Tropospheres, where all of our weather occurs, is where we live. Then above that we have the stratosphere, the mesosphere, and lastly the thermosphere. So learning to understand the atmosphere, the processes of weather and climate, as well as what extreme weather might be, especially as it is affected by Earth's motions, looking at our interaction with sun and seasons, looking at even climatic change, even human-induced climatic elements, greenhouse gas contribution and what is the long-term effect. So really learning the difference between day-to-day weather and long-term climate. We'll spend some more time talking about that, but weather is the day-to-day. It's hot, cold, wet, dry. And climate is taking at least 30 years of data and creating a general statement and saying, well, the climate in Las Vegas in July is generally hot. Is it possible that it can rain in July in Las Vegas? Of course it is, but that doesn't mean that generally it's going to be hot and dry, because we have this 30-year value of data that projects that. And by understanding that, we're able to project and predict tomorrow's weather and maybe even tomorrow's climate going forward, long term. And the last one that we introduce is astronomy, the study of our universe. So learning about our universe allows us to understand our personal planetary evolution. Where did Earth come from? Where is it going? What are we starting to observe about the future? So it's kind of like very philosophical. To understand yourself, you have to understand the environment around you, because that definitely is a reflection of what you are. So when we start to learn about other locations and watching the birth of stars and planets, well, what does that mean for our future here on Earth? Why are we striving so hard to find planets that can allow life to thrive? We're trying to see if there's anything else out there, but why does that intrigue us? Why do we have so many television shows and movies and sagas that are about the space and what's out there and how far and vast it is, and how much more we continue to learn about it? And hopefully we'll even get to cover, is Pluto really a planet or not? Why do people think it's not? So nonetheless, let us continue. So moving forward, so we're going to introduce the formation of our solar system. Earth and the surrounding planets formed around the same time. Long-term scheme, the process was a large what we have is the nebular hypothesis. The solar system evolved from an enormous rotating cloud, or a solar nebula, and that was about 5 billion years ago, when all the matter and mass was available for this to occur. Well, after the formation of this nebular hypothesis is that we bring us into, we can then talk about the formation of the Earth. The Earth planet itself is about 4.6 billion years old. That's when our story begins, once all that particulate matter was able to merge together and make a planet. So as the Earth formed, the decay of radioactive elements and isotopes from the center of the Earth produce heat. That ends up creating, and then also the decay of the material on our surface when it was still a molten planet, caused the temperature to increase. This gaseous material escaped and developed a basic atmosphere. Why are atmospheres important? Well, atmosphere keep out asteroids, meteors, particulate matter from extraterrestrial matter in that sense, but also trap gases in when that's important, because we wanted to be able to trap in oxygen, because that allows us the ability to survive. We'll learn a little bit more about where our planet, where we got our oxygen, where we received most of our water. We'll learn more about that in the future, but it's just to understand the formation of our planet. We're looking at a very, very long story. It's almost unbelievable for us to try to imagine what 4.6 billion years is. We'll learn a little bit more about that when we learn about geology, but nonetheless, big story. We actually can divide our planet into quote-unquote spheres, meaning realms, if you will. So I like this diagram. We often merge the hydrosphere with the cryosphere, but I label them as separate things just so we can talk about them that way. So the first one is the hydrosphere. That's water. Anywhere there's water on the planet is involved in the hydrosphere. So think back when you learned about the hydrologic cycle. We're talking way beyond just evaporation, condensation, and precipitation. When we start looking at the hydrosphere, we're going to learn about transpiration, how water works with plants, how it works with storage, how it looks with underground, and looking at different elements like that, moving into the cryosphere, adding in the element of ice. Where's it stored? How much is there? Why is it there? Is it getting bigger? Is it getting smaller? Is it thick? Is it thin? So understanding its process. We'll also be discussing basic geomorphology, looking at how the hydrosphere and cryosphere, water and ice itself, carve and shape our planet. We also look at the atmosphere again. That's another one of our spheres. It's very thin. It's only about 3.5 miles thick, yet it's able to protect us from everything, which is really, really, really important. It blocks out bad, negative and bad UV radiation that would otherwise cause us to burn. It keeps us at a relative temperature versus fluctuation of very cold or too hot. We also will introduce the biosphere, which is all life. That's everything from plants to you and me. And then we also get the geosphere, which is all rock. So we have these spheres that we introduce to kind of, make it more of a realm. I don't know, I learn better when things are kind of chunked together, when I can see that there's, okay, so these are all the things within the biosphere. These are all the things within the geosphere. These are all the things within the atmosphere. So again, I like this little diagram. It kind of gives an element. Geosphere, we can see there's plate tectonics involved. There's layers of the earth. We can see there's volcanics. We can see within the atmosphere, you've got all your different layers and special zones. So I guess kind of like this type of what I call putting it together. How do we put everything together? Well, since we mentioned it, we'll talk about it. We understand that we live on a dynamic planet, constantly changing. Understanding that we have these different layers of cores. When I think of the layers of the Earth, I also will talk about this in atmospheres. I think of salad dressings, like those homemade ones, where if they sit too long, they separate. So they separate based off their densities. Well, what if we could observe that idea here, looking at both densities and temperature? That will allow us to understand why we have these different layers within our Earth, moving from the inner core to the outer core to the mantle. Then looking at the asthenosphere, which is a plasticky zone that protects us and allows us to move around. The lithosphere, which is the rock material that we live on. And then we have our crusts, both oceanic and continental. We'll also learn the differences between these crusts. Oceanic crust is predominantly basalt. Continental crust is predominantly granite. Very different types of formations. Both igneous rocks, but both formed under very different environments. Another thing we can talk about is, well, how do we look at the Earth's surface? Well, we've got global grid systems. We look at the value of latitude, which is the distance north or south of the equator. When I think of latitude, I think of pizzas, the metal pan they cook them on. So all kinds of different sizes, yet they're all circles. Well, that's kind of what latitude is. Latitude is the distance north or south of the equator, but drawn all the way around. So they're lines that kind of work themselves as disks around the Earth. Well, then you have longitude, which is the distance east or west of the prime meridian. Well, longitude is like an orange. So they intersect at the north and south poles, but create a meridian or a half circle. So because you have these two different lines that are running in different directions, we can create intersecting points, which is going to be part of your grid system. We'll talk more about that later. We also look at cartography. That is an art in its own. It represents an area of the Earth by using data and distortion. We look at topographic maps, geologic maps. How do we view the landscape? Most of you probably don't even own a map or a Thomas guide or anything like that, but you have experienced true cartography, especially if you play video games. A friend of mine works for the World of Warcraft world, and her job as a geologist is to help them design their landscape and to create a map that is believable to its consumers, you. So if you're playing these video games and they're in landscapes that have volcanoes and trenches and volcanic ranges and everything in between, that's because it's been detailed by an earth scientist, because we've been able to represent a landscape that is probably functioning, that's true, so that way you believe it. Because let me tell you, if you played a video game in a landscape that did not make sense, the game will not make sense to you. And you probably think about that. Have you ever played a game that you're looking at and it's like, well, why is this? I'll give you an example. I knew a student who was part of a video game design program, and they were trying to build this video game where it was an island, a very small island, and the island was like a pie, and it would be divvied up like, this is going to be the desert, this is going to be the mountain, this is going to be the rainforest, and it's like, well, it looks good on how you're trying to do it, but geologically and looking at it from as an earth scientist, that's the way they had it designed was not going to work in a real environment, and so therefore it doesn't make it very believable. So how do we interpret it? How do we make these locations believable? And that's understanding the process and understanding the spheres and how they interact with one another. Then we'll look at systems. Well, what is a system? An institution is a system of people that work together to make progress. So a system is any size group of interacting parts that form a complex whole. So you as a student are part of a system, a bigger system, because yes, you're a student and I'm an instructor, but I'm still going to learn from you. We're part of this system. We're supposed to work together to create a bigger resolution and to create more information and more data. Now, there are two types of systems. There are closed systems, which means they're self-contained, which means they don't take anything in and they don't put anything out. And we also have open systems that allow energy both in and out of all times. So we have closed systems and open systems. Now I bring this up because what are some Earth systems? What are some systems that you think could be open or closed? In fact, I'll give you a hint. A lot of people argue that there's no such thing as a closed system, right? Let's think of an open system. Vegetation. Well, plants require sunlight. They require that short-wave radiation in order to go through photosynthesis. They also require carbon dioxide because then they produce oxygen. So they are taking in and putting out. You are an open system. You need food so you can then gain the calories, which then give you the ability to do work, to have energy. So then by having energy, you are able to move around and you produce heat. So you are also an open system. Often, as an example, what about closed systems? People think that terrariums, like this guy right here, this is a closed system. You put the plants, you put everything in there, a little bit of water, you seal it, put a cork in it, and then it's done forever, right? You never have to deal about it again. Well, but it still requires sunlight. So that's the argument. It's like, well, it still requires sunlight, but everything else is trapped inside. So it's not able to be open, but is it really closed? So it's kind of like one of those thought processes. Well, when you come up with other closed systems, how do you do that? Well, we can use what we consider the scientific inquiry, which is really a very important method, as anyone should be able to use this system. This is how we should think. We have an idea. That idea can either become a hypothesis, which is tentative or untested, or it will be a theory, which is tested, confirmed, and supported by the majority. So when people say, well, I have a theory about this, they're actually not correct in saying that unless it's been tested, confirmed, and agreed upon by the majority of people who are also specialists in that topic. They're more coming up with a hypothesis, right? Well, I think that, these are the winning numbers for the lotto. Well, that's a hypothesis. You don't have a theory for that. So when we talk about the theory of evolution or the theory of plate tectonics, a theory means, that word means it is. It is plate tectonics. It is evolution because we have tested it, we have confirmed it, and it is supported by the larger group. Scientific knowledge can only be gained by collecting data, developing research questions, and conducting experiments. So that is very, very important because often we, as a society, jump to conclusions. We see something on social media and then, we just believe it. It has to be this. We don't question things. And I think it's so important that we get out of that habit and learn to question and be like, well, I don't understand. Please explain to me. Think about with any conversation, people, they say on first dates, never bring up politics or religion, right? But I don't think it's a bad thing, especially if you want to learn. I want to learn about your politics. I want to learn about your religion. I don't think you're wrong, and I'm not going to argue if you're right. I want to learn and be able to ask the right questions so I can understand what it is that you believe or what you stand for or what your methodologies are. So let's use this as an example. This is your classic scientific inquiry diagram. You first ask a question, then you do research. After you've done research, you construct a hypothesis. Then you work through it, and then when you get to the end, then you can state that it is a theory. So let's ask a question. I think that people who are really tall have to wear bigger shoes. That is my thought. So I need to do some background research. Well, some basic background research. I could go to Nike for the weekend and hang out at the store and kind of peruse people and go, well, let's see, based on their height, what type of size, what shoes are they buying? Are they buying these really big, size 12 or 13 shoes? Are they buying more like a size 4, 5, or 6? So then based on that observation, I can say, I think I've got an idea here. I'm going to construct a formal hypothesis that's going to require me to collect data, formal data, that's going to allow me to do some background research for either new or future project, and then I need to start asking questions so I can form it even better. So I'm going to move down forward. So I'm now here. I'm just going to jump straight to here. I want to test it. So what if I ask every student I meet, how tall are you and what size shoe you wear? Well, I would need that would probably work. I don't think people would have a hard time giving me that information. I think if I was asking how tall you are and what you weigh, I don't think that procedure would work, but I think asking for shoe size would be okay. So I would get a lot of data. I'm not talking like 20 people, I'm talking about 300 at least. Then, if that data is working, yes, I'm going to analyze that data to try to come up with some solutions. So what I would do is take that data and I'd put it in Excel and I'd create a trend line. I'd plot it to see where everyone is. Then I would create a trend line, and along that line I'd get an idea that, okay, I'm starting to see the taller people are the larger the shoe. That's great. So then how would I test my results? Well, I would, after I collect all my data, I would pick a random person and I would use just half of their data. I go, well, how tall are you? And then they would say, well, I'm 5'11". Well, then I would plot 5'11" on my trend line. I would say, do you wear size 10 and a half shoes? And if they go, well, I do. How did you know? They would say, then I tested my data and I think I can start thinking that this could be a true hypothesis. So then I would start checking other people against my trend line, and then I would either have to agree, I'd have to accept, or reject my initial hypothesis. If I accept it, then I can communicate my results, and then we can decide if this is a hypothesis that is going to work into a theory, or if I reject it, I go back. And let me tell you, there is nothing better than rejecting your hypothesis. I know that sounds weird. I think failure can be such a great experience because, hear me, because then it gives you learn something, so you have results. Okay, I know that what I said was wrong, but I got some other results. So how can I use those results to solve something new or different? Failure in science is so incredible because it gives you the chance to do the work again and to try over and test new theories. That being said, failure can also be negative if you don't move on from it. So nonetheless, it's really exciting in earth sciences for us to be able to test these hypotheses and to then turn them into theories, and then to continue to test the theories to make sure that they're valid, to make sure that it works, and to make sure that it's true. And they will, as long as we constantly question our system with thinking questions, critical thinking questions, we get into a better location and situation. Well, I know it was a lot, but again, this was just introduction to what everything we're going to be talking about for the rest of the term. So I really appreciate your patience, and I look forward to learning more with you, and we'll talk soon.